All right, our next volume that we're going to look at is when you have perpendicular cross sections along a base. So we call a cross section to be the intersection of a plane with the solid. So if you had a cylinder, and let's just say like you only have half of it so that it can lay nice and flat there, notice the cross section of that cylinder, or that half cylinder, would be a semicircle, right? So like if you were to look at like what this intersection of that plane would be, it would be a semicircle. And so if we wanted to find the volume of a cylinder, then we always do the area of the base times the height of the cylinder, which for a normal cylinder would be pi r squared, and then times h. Or in this half cylinder, half of that would be 1/2 pi r squared h for this little half cylinder can that we have here. And so I want to show you how to use integration in order to generate that volume. So I'm going to pull that picture back up for us. This is our x-axis, and we're going to say our y-axis cuts like this. And so our radius here is what goes around. So this would be positive r. This would be negative r. And then the height of the cylinder, I'm going to go from 0 to h. Now that radius stays the same the entire time. So my radius is constant. Sometimes we'll end up having that your radius is a function of x, if you will. So it might change, but this is the line like y equals positive r. And so it's going to be a constant that we're going to have here. So when I'm looking at the area of my base, I have 1/2 pi r squared. And then I want to integrate that. I want to add all of those up from 0 to h of the 1/2 pi r squareds with respect to x. Like this little, like the area and then the height of just that little piece, right, is dx. And then you add up all those pieces from 0 to h. Well, this is just a number. It's a constant, and it's a constant down the whole entire thing. So when I take the antiderivative, I have 1/2 pi r squared times x from x equals 0 to h. Again, because 1/2 pi r squared, r is a constant given to you in the problem. And so if I were to take the antiderivative of 4, I'd get 4x, right? -10, -10x. So this is just a number, and then times x for our antiderivative. I'm going to plug in h and 0, and you'll see the volume for that half cylinder is exactly what we got up here. Same exact thing. And if you wanted the whole thing, you just multiply by 2, and you just have double this, right? All right, let's look at a pyramid. And I want to try to draw this as best as I can. So normally when we find a pyramid, you look at it this way. Right? And so your like base of your pyramid would be here. And the volume of the pyramid is 1/3 the area of the base times the perpendicular height. Okay, the perpendicular height inside here. If the pyramid has a square base, then we'll say if this has side length a and height h, then we'd have 1/3 a squared h. But we're going to use they call it the slicing method in this textbook, but the cross sections in order to do that. We're going to do something very similar that we just did with that cylinder, and we're going to make an axis here. So that's going to be x. So I'm going to flip this around. So my sides kind of go like this, and then my square is like that, okay? Because that x-axis is going. All right, now I know this whole side length here is A, and I know that this goes from 0 to H. But a question then becomes is like, well, what is this shape? It kind of looks like the volume of revolution that we were doing before, but it's not a revolution. Revolutions are circles. So I need to figure out, we were looking at circles before, I need to figure out what just a representative piece in here might look like. Okay. Now, this length goes from 0 to H, so I'm going to call this just an arbitrary X. And then I'm going to call this height S for side. Okay. Now, it is true that proportionality exists here. So S over X must be proportional to A over H, because anywhere that I choose that X value, it must end up following that same trend to whatever A over H is, kind of using that similar figures rationale from geometry here. So again, this side length over like its position in the pyramid turned on its side here must be proportional to the overall length over H. Now that side length, that's what I need to figure out, and I want it to be a function of X, and it's important to know A and H are numbers. So I know that the side length is proportional to A over H times X. Now, another thing that you could do if you are not really keen with the proportionality, okay, this length here is 1/2 of A. And so the slope of this line is rise over run, 1/2 A over H. And so this S, but only half of S, right, would be, or X, I should say. I could say that half of S, or half of my Y, is equal to that slope times X with the y-intercept of 0. And so those halves would cancel, and you'd end up getting the same thing here. So either you could use algebra to kind of figure out using the slope, or you could use similar figures and geometry in order to figure that out. Okay, so that means that a representative little piece in here has a width of dx. So S squared times dx is what's going to end up giving me the area of one piece, because that's or the volume, excuse me, of one piece, because it's a square. So S times S, S times S, and then a volume piece of dx. So I'm going to add that up from 0 to H. S squared dx. But I know that S is equal to A over H times X. A squared over H squared can come out of your parentheses. I then have 1/3, so I'm going to put a 3 here, X cubed from 0 to H. I end up getting 1/3 A squared over H squared times H cubed, and these simplify, and you can see that is the equation of the pyramid.